Electromagnetism, we'll do introduction. So static field, electromagnetic field, field associated with media, force, torque and energy, LCR circuit, transmitted line and waveguide, wave in and out of the medium, plasma physics. Equation conversion, SI to Gaussian unit, epsilon goes to 1 by 4 pi, mu goes to 4 pi by c square, B goes to B by c, but E don't change, J also not change, rho do not change, phi do not change, sigma do not change, polarization do not change, relative epsilon and relative mu do not change. But D will change, D to dy 4 pi, H to ch by 4 pi, A will A by c, M with cm. Static field, electrostatic potential E equal to minus delta phi, nabla phi, potential difference phi A phi minus phi B equal to E dot dl from A to B. Poisson equations, Poisson delta 2 phi equal to minus rho by epsilon. Point of charge, so electric field potential and electric field can be calculated like this: Q by 4 pi epsilon 0, 1 by the distance. For electric field, that will be Q by 4 pi epsilon 0 times R unit of R square. Field from a charge distribution, in place of Q we will replace with rho times d tau with a integration sign. For magnetic scalar potential, B is the magnetic flux density equal to mu times nabla of phi m. Phi m is the magnetic scalar potential. So magnetic scalar potential phi m equal to I omega by 4 pi. Omega is the loop solid angle, I is the current. Biot-Savart law, B equal to mu 0 I by 4 pi times dl sin theta by r square, or we can write like this vector form. Ampere's law, curl of B equal to mu 0 j. Ampere's law integral form, just we will take the Stokes theorem, then B dot dl integration over a loop will be mu 0 I. So how much current it will pass through the loop, it will be sum of total I. Now capacitance for a sphere of radius A, C equal to 4 pi epsilon times A. For a circular disc, 8 of A epsilon 0 epsilon. For two sphere of radius A, we will have 8 pi epsilon A into ln 2. For a circular solid cylinder, we will have that formula. For nearly spherical surface, we will have this. For a cube, we will have these following values. Between concentric spheres, we will have 4 pi epsilon AB divided by B minus A. Between a coaxial cylinder, 2 pi epsilon by ln B by A. B is greater than A. Between parallel cylinder, pi epsilon by ln 2 d by A. Between parallel coaxial with circular disc separated by d, epsilon pi a square by d plus epsilon A ln 16 pi by d minus 1. Inductance for n-turn solenoid will be L equal to mu n square A by L. Mu n square A by L. For coaxial cylinder, mu 0 by 2 pi ln B by A. Coaxial cylinder. For parallel wire of radius A and separated 2D, we get mu 0 by pi ln 2D by A. For a wire of radius A bent to a loop of radius B, then mu 0 B by ln 8b by a minus 2. Now electric field for a uniform charge pair, mu by 4 pi epsilon 0 r a0 square a cube. Whenever r is less than a, but when r is greater than a, then q by 4 pi epsilon 0 by r square with r vector. Uniform charge disk, then q by 2 pi epsilon 0 a square z by mod z minus z by square root of z square plus a square. Line charge density, so E equal to lambda by 2 pi epsilon 0 r square or 2 lambda by r square. Electric dipole moment, E radial component p cos theta by r square, 2p cos theta by r square 1 by 4 pi epsilon 0. So this is radial. For angular direction we have p of sine of theta by r cube. Sorry, this will be also r cube. Charge sheet on a surface will be E by 2 epsilon 0. Now magnetic fields for n turns with current I will have B equal to mu 0 n I inside, and outside we will have 0. In per cylinder of I current at radius I will have mu 0 IR by 2 pi a square whenever R is inside A, or other outside mu 0 I by 2 pi R. It will decrease with R, but here inside it will go as R, but outside it will go like 1 by R. This is R equal to A. Magnetic dipole moment B equal to mu 0 by 4 pi times 2m cos theta by r cube. For B theta we will have m sin theta by r cube. Circular current loop of n turns of radius A equal to mu 0 ni by 2 times a square by a square plus z square to the power 3 by 2. For state solenoid of n turns, mu 0 ni by 2 cos of alpha 1 minus cos of alpha 2. Alpha 1 is the alpha 1 this angle, and alpha 2 is the second angle. Whenever the cylinder solenoid is infinity, then this will be 1 minus 1. So it will have mu 0 ni. This is the magnetic field inside this solenoid. So real charge q at a distance a, then image points and the image charges. So B from a conducting plane, then minus B, and image charge is q. B from a conducting sphere of radius a, then a square by B minus QAB. B from a plane dielectric boundary seen from free space equal to minus B, and Q times epsilon r minus 1 epsilon r plus 1 seen from a dielectric B, and 2Q by epsilon r plus 1. Electromagnetic fields. So conservation of charge, this is the continuity equation. Magnetic vector potential B equal to curl of a electric field from a potential E equal to minus grad of phi minus del A del T. Coulomb Gauge condition, divergence of A equal to 0. Lorentz Gauge condition, divergence of A plus 1 by c square del phi del T equal to 0. Potential field equation, this is the equation 1 by c square del 2 phi del 2 del T2 minus nebula square phi equal to del rho del epsilon. Again similarly for A, but with the source term is mu 0 j. Expression for phi in terms of rho. So phi equal to 1 by 4 pi epsilon 0 integration of rho d tau by r minus r dash. For A, mu 0 by 4 pi epsilon 0 j d tau divided by r. For Leonard Wishart potential, electric potential of a moving charge, phi equal to q by 4 pi epsilon 0 1 by r minus v r by c. For magnetic vector potential of a moving point charge mu 0 by 4 pi epsilon 0 4 pi, then qv divided by r minus r dot v by c. This is the magnetic vector potential. Now Maxwell equation, divergence of E equal to rho epsilon, divergence of B equal to 0, divergence of E equal to minus del B del T, curl of B equal to mu 0 j plus mu 0 epsilon 0 del D del E del T. So this is the integral form for the first Gauss equation. Integration of surface is 0, integration of loop of electric field equal to d phi dt, and integration loop equal to mu 0 I mu 0 epsilon 0 del E del T ds. Now relativistic electrodynamics, Lorentz transformation of electric and magnetic field, E parallel equal to E parallel at different frames. Transformation rule, E perpendicular equal to gamma times E plus curl of B perpendicular, B parallel also B parallel. B perpendicular is gamma times B minus B cross E by C square perpendicular. Lorentz transformation of current and charge density, rho will be changing, gamma rho minus V J by C square, J perpendicular will be same, J parallel will be gamma J parallel minus V rho. So Lorentz transformation of the potential fields, phi transform to phi gamma phi minus V A parallel, A perpendicular will be same, A parallel will be gamma A parallel V phi by C square. 4 vector notation, J is the 4 vector J equal to rho C by J, rho C comma J. A is phi C comma A. So this conclusion has been drawn from the earlier expressions. And D'Alembert operators, del box square equal to 1 by c square del 2 del t2 comma nabla square. So the final expression is nabla square box square A equal to mu j in terms of 4 vector notation. Field associated with media for polarization, definition of electric dipole, P equal to Q dot Q times A. So P is the Q times the distance between the charges. Generalized electric dipole moment, P equal to R times rho dt, d tau. Electric dipole potential, phi equal to P dot R by 4 pi epsilon 0 R cube. Dipole moment per unit volume, P equal to NP, N is the number of dipole per unit volume. Induced volume charge density, rho equal to minus del divergence of P. Induced surface charge density equal to sigma induced equal to P dot S cap. Now definition of electric displacement, D equal to epsilon P plus epsilon E plus P. Definition of electric suspensibility, P equal to epsilon xi E of E times E. Xi E is electric suspensibility. Definition of relative permittivity, epsilon R equal to 1 plus xi E, D equal to epsilon E. Atomic polarizability, P equal to alpha E local, and depolarized field ED equal to minus ND P by epsilon 0. ND is the depolarization factor. For sphere it is 1 by 3. 1 is for thin slab, 0 for thin slab perpendicular to P, half for long circular cylinder. Clausius-Mosotty equation, n alpha by 3 epsilon equal to epsilon r minus 1 epsilon r plus 1. Magnetization, definition of magnetic dipole moment, dm is the dipole moment equal to ids. Generalized magnetic dipole moment, m equal to half of r cross j d tau. Magnetic dipole potential phi equal to mu by 4 pi epsilon 0 m dot r by r cube. Dipole moment per unit volume m equal to n times small m. Induced volume current density J equal to curl of m. Induced surface current density m dot cross S cap. Now definition of magnetic field strength. So B equal to mu 0 H plus m. So m can be written like xi of H of times H. This is xb is the magnetic susceptibility equal to xi h by 1 plus xi h. So definition of relative permeability. So B equal to mu h. So mu r equal to 1 plus xi h, that is equal to 1 by 1 minus xi b. Paramagnetism and diamagnetism. Diamagnetic moment of an atom m equal to minus a square by 4m times z times average of r square times b. B is the magnetic flux density. Intrinsic electric magnetic moment m equal to minus e by 2m g times j. G is the Lagrange factor, that equal to 1 for orbital momentum. Langevin functions Lx equal to x by 3, x equal to x is less than 1. Classical gas paramagnetism, average of m equal to this n m0 of L m0b by kt. Curie law, xi of h proportional to 1 by t. This is Curie's law. Curie-Weiss law, this is xi h proportional to 1 by t minus tc. Now boundary condition for E, D, B, H. E parallel is continuous, B perpendicular is continuous, but electric displacement S dot d2 minus d1 is sigma. So perpendicular component of d2 minus d1 perpendicular is sigma. Again perpendicular of h2 minus h1 equal to js. Parallel component of h2 minus h1 of parallel component will be js. Surface charge current density. Force, torque and energy. Electromagnetic force and torques. Force between two static charges 1 by 4 pi epsilon 0 q1 q2 by r square. Force between two charge carrying current, then mu 0 by 4 pi epsilon 0 4 pi times I1 I2 by the distance between two square times dl 2 cross dl 1 cross r12. This is the force. So this will indicate the direction. It will be attracted or repelled. Force on a current carrying element in a magnetic field, delta F equal to q v cross b, or you can write I dl cross b. Force on a charge q e plus q v cross b. Force on a electric dipole p f equal to p dot nabla times e. Force on a magnetic dipole m dot nabla of b. Torque on a electric dipole p cross e. Torque on a magnetic dipole m cross b. Torque on a current loop g equal to il times r cross dl cross b. Electromagnetic energy U equal to electric energy plus magnetic energy 1 by half of epsilon e square plus half of b square by mu. Energy density of a media half of d dot e plus b dot h. Energy flow or Poynting vector n equal to e cross h. Mean flux density n equal to proportional to omega to the power 4. Total mean power equal to omega equal to W equal to omega to the power 4. Self energy of a charge distribution U total equal to epsilon phi r times rho r d tau to the power times half. Energy of a assembly of capacitor we'll have C1J V1Vj. Just of a assembly of inducer, we have same formula, just replacing L and I. Intrinsic dipole in an electric field, U equal to energy of the dipole equal to minus P dot E. Intrinsic dipole in a magnetic, then M minus M dot B. Hamiltonian of a charged particle in a electromagnetic field, so H equal to P minus QA square by 2M plus phi of Q, phi times Q. LCR circuit, current equal to I dq dt, Ohm law B equal to IR, Ohm law in field form J equal to rho sigma E, resistivity rho equal to 1 by sigma equal to R times A by L, or R equal to rho L by A. Capacity Q equal to CV, then current through the capacitor, so dq dt equal to C dV dt. So current through a capacitor, self inductance phi equal to Li, L is the self inductance, voltage across the inductance, that equal to d phi dt equal to L di dt. So d phi dt equal to minus of V. So from that V equal to minus L di dt. Mutual inductance L12 equal to phi 1 by I2 equal to L21. Coefficient of coupling L12 equal to K times L1 times L2 square root. Linked magnetic flux through a coil, phi equal to N phi. Resonant LCR circuit, phase resonance frequency omega 0 square equal to 1 by LC. For a series, for parallel 1 by LC minus R square by L square. Tuning delta omega by omega 0 equal to 1 by Q. Q is the quality factor equal to R by omega 0 L. The quality factor Q equal to 2 pi by stored energy by energy loss per cycle. Energy in capacitor, resistor, inductor and resistor. For capacitor we have Q equal to U equal to half Q dot QV, or Q equal to CV, so CV square you can write. Energy stored in inductor Li square, half of Li square. Power dissipated in the resistor W equal to IV. Relaxation time tau equal to epsilon R by sigma. Sigma is the conductivity. Electrical impedance, for series we have total resistance equal to sum of the resistance. In parallel we have sum of the reciprocal to the power minus 1. For capacitor 1 by I omega C. For inductor I omega L. So impedance Z, inductance L, conductance 1 by R, admittance 1 by Z, capacitance C, resistance R. Of real of Z, reactance is imaginary part of Z, and suspectance is S equal to 1 by X. Kirchhoff's current law equal to sum of the current at a node equal to 0. Voltage, sum of the voltage over a loop is 0. So transformer, we have the initial coil, primary and secondary coils with N1 and N2 turning. So turning ratio small n equal to N2 by N1. Transformation of voltage to current, V2 equal to N times V1, I2 equal to I1 by N. Output impedance equal to N square Z1, and input impedance equal to Z2 by N square. Star delta transformation, star impedance and delta impedance is like this. Transmission lines and waveguide, loss free transmission line equation, delta V by delta X equal to minus L di dt, and delta I by delta X equal to minus C dV dt. Wave equation for a lossless transmission line, we have these two formula. d2v dx2 times 1 by lc equal to d2v dt2. Similarly for I also 1 by lc d2i dx2 equal to d2i dt2. Characteristic impedance of a lossless line, zc equal to root over lc. Characteristics of impedance of lossy lines, zc equal to root over of r plus I omega l g plus I omega c. Wave speed along a lossless line, phase velocity and group velocity equal to 1 by root over of lc. Input impedance of terminal lossless line equal to zi have this following complex form. Reflection coefficient from transmitted line equal to r. Line voltage standing wave VSWR equal to 1 by r, 1 plus r by 1 minus r. Transmission line impedance, coaxial lines have this formula, ln b by a. Open wire feeder equal to ln l by r. Pair strip as proportional to d by omega. Micro strip line have square root of 1 by omega h plus 2. Waveguide have kg equal to wave number in the guide equal to omega square c square by omega m square pi square by a square n square pi square by b square. Guide cutoff frequency omega mu equal to c times of m by 2a square plus n by 2b square. Phase velocity cutoff vp equal to c by 1 by nu c by nu whole square. Group velocity above cutoff vz equal to c square by vp. Wave impedance and ztm equal to z0 to the power 1 minus nu c by nu whole square. For transverse magnetic modes, for transverse electric modes, we have z0 divided by 1 minus mu c by mu to the power whole square. Field solution for TE mode, Bx, By, Bz have this following form. For TM mode, we have Ex, Ey, Ez in the following form. Here for transmitted electric mode, Ez equal to 0. For transmitted magnetic mode, Bz equal to 0. Wave in and out of the medium, electric field equal to nabla square E equal to 1 by c square delta 2 E by dt2. Similarly, magnetic field have the same expression. Refracting index eta equal to 1 by equal to square root of epsilon r mu r. Wave speed v equal to 1 by mu times epsilon to the power minus to the power half. Impedance of free space z0 equal to mu 0 by epsilon 0 equal to 376.7 ohm. Wave impedance z equal to E by h. So this is the radiation pressure. So for radiation moment density, isotopic radiation, spectral reflection from extended source, from a point source, we have these formulas. For antenna, we have spherical polar geometry. So field from a short electric dipole moment in a free space, we have ER, E theta, E B phi as the following expression. Radiation resistance of a short electric dipole moment in free space, R equal to or proportional to L by lambda to the power square ohm. Beam solid angle omega equal to Pn of d omega's integration over 4 pi. Forward power G0. Antenna efficiency A equal to lambda square by omega A. Power gain of the short dipole, beam efficiency, antenna temperature, reflection, refraction and transmission. So parallel incident line, so in that case we have theta incident equal to theta reflection. Snell's law, eta I cos sin theta I equal to eta t sin theta t. Brewster law, tan theta equal to eta t by eta I. So Fresnel's equation of reflection and diffraction, r parallel equal to sin theta 2y minus sin theta t, sin 2 theta t by sin theta 2y plus sin theta 2t, sin 2 theta t. T parallel will have t cos of theta I sin theta t, 2 sin 2 theta I sin 2 theta t. R parallel equal to small r parallel square, t parallel equal to eta t cos theta t by eta I cos theta I, t parallel square. R perpendicular also have this formula, r t perpendicular and r perpendicular, t perpendicular has this following expressions. Coefficients of normal incidence, reflection equal to eta I by eta t, eta minus eta t by eta I minus plus eta t to the power square. T equal to 4 eta t by eta I plus eta t whole square, r plus t equal to 1. Propagation in conducting medium, electric conductivity, sigma equal to n e mu equal to n square by m e tau c. Refractive index of a ohmic conductor, eta equal to 1 plus I sigma by 4 pi nu epsilon 0 to the power half. Skin depth of a ohmic conductor, delta equal to 1 by square root of mu 0 sigma pi nu. Electron scattering processes, Rayleigh scattering, sigma r equal to omega to the power 4. This is Rayleigh's cross section, sigma r equal to Rayleigh cross section. Thomson scattering cross section, theta sigma t equal to proportional to r to the r e square, classical electron radius. Inverse Compton scattering, p total equal to electron energy loss rate equal to 4 by 3 pi t sigma t cu radiation gamma square b square by c square. Compton scattering, the change is lambda equal to h by mc times 1 minus cos theta, that is important one. Compton scattering. Now h nu dash equal to m e c square by 1 minus cos theta plus 1 by epsilon, and quad phi equal to 1 plus epsilon tan phi by 2. Here epsilon is h nu by m e c square. Now Klein-Nishina cross sections, sigma ke has this following form. Cherenkov radiation, Cherenkov cone angle sin theta equal to cy eta v, radiation power p total equal to e square mu by 4 pi with an integration 0 to omega c 1 minus c square b square eta square times omega d omega. Now plasma physics, one plasma, Landau length, electron dy length, dy screening, dy number, relaxation time, characteristic electron thermal speed. For electromagnetic propagation in cold plasma, plasma frequency is this: plasma radiation reflective index, plasma dispersion, plasma space, plasma group velocity, cyclotron frequency, Larmor radius, mixed propagation mode, and Faraday rotation. Magnetohydrodynamics, sound speed Vc equal to gamma p by rho to the power half, Kelvin speed b by mu 0 rho to the power half. Plasma beta equal to 2 Vc by gamma Va square. Direct electric conductivity, all electric conductivity, generalized Ohm's law, J equal to sigma d E plus B cross B, sigma H B cross E plus B cross B. Resistive MHD equation, del B del T equal to curl of B cross B plus eta nabla square B. Delta B delta T plus B dot nabla B minus equal to minus P by rho 1 by mu rho curl of B cross B minus plus mu nabla square B plus nu nabla of divergence of B plus G. Shear alpha dispersion relation is this, and magnetoresonance dispersion relation has the following form. Cyclotron radiations, power of radiation by single electron, average over pitch angle, single electron emission spectrum, characteristic frequency, spectral function, Brachey-Strolong, single electron and ion, dW d omega, thermal Brachey-Strolong radiation for Maxwellian distribution, dP dB by d omega, dP dB equal to this formula. So that's it.